Chapter number 7, work and energy. So it's the long journey from the time when we started with the, what happened? Oh my God. Was it just one bird? But the sound was loud. Okay. So we started with kinematics, introduced how the objects move, what quantities explain it, speeds, velocities, accelerations. Then we moved on to dynamics of that kinematics, that if the object is moving, what could be responsible for that motion, and the forces are. And then we put the forces together, we used the Newton's second law, and we came up with the relationship of the force with the motion of the object. Now we are moving on. That's the next step. After the forces are introduced, there is something else which comes into play when you're talking about the physics of the moving objects. There is always energy involved too. We all have already some idea about it. If the object is moving, it should have some energy. If the object is sitting on the table, it should have some energy. All of us have some sort of energy in us. But the definition of energy in physics, that comes from work. If the work is done in a system could comprise of a single object or multiple objects. If the work has been done, that would appear as the energy of that object or that system. The work definition in physics is not same as the work definition that you already know. What you already know? If I ask you to define work, how are you going to define it? No, that's physics definition. What is work definition that we use in our everyday life? Huh? Yeah, doing some task. Okay, I have worked all day. I have been working 2 jobs, something like that, right? That's how we talk about work. In physics, we talk about forces, and if there is a force, there must be some distance traveled in the direction of force. So definition of work from physics perspective is the force multiplied by the distance in the direction of force. That is the basic definition for work. If the distance covered, or you can see the word displacement too, if the distance covered or the displacement is not in the direction of force, then this is not the work done by that particular force you are talking about. Okay? You only want to discuss the force, and if the object has moved in the direction of force, yes, the object has done some work, or some work has been done on the object. Now this is the definition in words. Mathematically, for example, you have a crate sitting on the floor and you apply some force, and this crate has moved to a new position here. Let's say its distance covered, or in this case distance and displacement are the same. If the distance covered is d, then we can define work as force multiplied by distance. Correct? This is how we define it. Is the distance in the same direction as force, or displacement is in the same direction as force? Yes. Correct? We are going to see several examples where the forces and the direction of motion are not the same. Okay, but in this case where we are defining the work, initially we are making the object move in the same direction. This force is a constant force. That means the object is not accelerating. Okay? Now pay attention to the word not accelerating. That means it's moving with the uniform speed. Speed is not changing. It has just gone, or even if it has acceleration, it's really small. This is the work done. We are defining the formula for work done by the force, which is constant throughout this motion. What if the force acts on this object at some angle? What should we do here now? Yes. Now, will this force, is the displacement in the direction diagonally? No, right? Is the object moving horizontally? Yes. There is no vertical motion, it's just horizontal motion. So you have to take the horizontal component of the force as well. You drop the perpendicular, get two components, right? Which one is in the direction of displacement? F cosine of theta. So now your formula here will F cosine of theta times d, or we can put it together as Fd cosine of theta. That is the complete definition of work, where theta varies from 0 to 180. Complete definition, yes. This is the what I already had here was F D. That is a special case. What is that special case? 1 theta is 0. Because cosine of 0 will be 1. This is a special case. This is the maximum work done if the force and the displacement are in the same direction. Positive work done. Could be from 0 to 180, it could be 90, it could be 180, it could be any value. What if could you guess what is the minimum value of theta? Cosine of theta? 0. When is it going to be 0? When cosine theta is 0? When they are perpendicular, right? So 1 theta cosine of 90, this is 0. Minimum work done or no work done. Good? If theta is 180, W is equal to F D cosine of 180. What is cosine 180? Negative 1. Negative work is done. Positive work results in increase in energy. Negative work results in decrease in energy. So if the positive work is done, is this a positive work right now or negative work? This force is doing a positive work. Could there be any force there which could do the negative work? Friction. Friction always does the negative work because you always have to work against the friction to make the object move. Are we good so far? Easy to follow? If the force and displacement parallel, maximum work is done and positive work is done, energy will increase. If they are opposite in direction, negative work is done, the energy will decrease. And if they are perpendicular to each other, force and the displacement, if they are like this, displacement here, force here, there is no work done absolutely. Zero work done. Any example of zero work done that comes to your mind? Huh? With the example where the object is moving and there are forces on it too, but still it's not doing any work. Walking on the ground? Okay. That is good. Yeah. If it's on the flat surface, yes. Good. Now, what force is acting on you? Gravity. Very good. If I'm holding a bag, if I'm holding a book, and I'm walking with the book, the weight of the book is acting downward, displacement is forward, there is no work done. It's very similar to what you said. So the gravity is acting downward and the displacement is forward. They both are perpendicular to each other. There is no work done on the book. However, if I move the book up or down, I am doing some work. Okay? Yes, exactly perpendicular. The unit force is Newton, distance is meter, Newton into meter. That is the fundamental unit or SI units, but work is represented as joules. Joules is new to you. So 1 joule is equal to 1 Newton into meter. Joule is also the name of the scientist. Joules are used, we can use J as a symbol. So for example, if you want to say an object has done 13 joules, joules would represent the work done and the energy too. Okay, from now on, any kind of energy we define, any kind of work we talk about, okay, no matter how different it looks, if it is work done, it's always going to be measured in joules. Let's look at one example where there are multiple forces acting on a single object. Flat surface, constant force, at 30-degree angle, and the displacement as the result of application of this force is 5 meter. This much it has moved under the influence of that force. Force applied is 1.20 times 10 to the 2 newtons. And it's not a frictionless surface. Tell me what forces are missing there. Which way it should be? Looks good? What kind of friction is that? Kinetic friction. What else? Normal force and the gravity. Now the picture is complete. Kinetic friction is 45 Newton. That is also given. So you calculate the work done by the force. What you want to know is the net work done. Net work done. Okay, that means you have to include all the forces, okay, and the displacement associated with them. So forces, there are 4 forces. First force is the actual force. Has anyone solved it already? Sorry? 300 by multiplying them. I got a different number. What did you, did you do cosine correctly? You, yeah. You probably did half of it. So it's 520 joules. Good? What is the work done by the friction? Ft cosine theta 45 5 cosine of 180. What's the answer? $195? $225? Maybe I plugged in the wrong. Yeah, negative 225 joules. Everyone else follows? Good. Work done by the normal force? Normal force is Fd cosine of 90 degree, that is 0. Work done by mg is also 0. They are not doing any work to it. So net work would be equal to, adding them all, 520 joules plus 0 plus 0 plus negative 225. Just subtract them. That will give you the final net work done. Yes.
Could you not just take find your net force, so go ahead and figure out what your force along the x-axis is, and then subtract the force of friction, and then do your multiplication?
Treating them separately, like forces, some of the forces are vertical, some of the forces are horizontal. You will end up with the same thing. But so you are saying that treat the vertical forces together. So what is it going to give you? If you have the net force vertically, that's going to give you 0. So it's also going to give you a 0 work done. But that's putting the total force as 0. That's another way to approach the solution. That is correct too. Nothing wrong with it. But it should not give you, however, when you do the horizontal forces, in case of horizontal force, you have this force and this force. If you get the net force, the angles are different. It is not a very good way to proceed. It's not going to affect your answer for vertical direction because there is no motion in that direction. But horizontally, if you do the net force horizontally, so the net force would be this F cosine of theta minus, if we take F cosine of theta. If you do not take F cosine of theta, then it's going to be wrong. Okay, if you just correct. You cannot simply subtract them. You have to include the angle somehow.
That's how I did it, and I got it.
Okay, good. But you did take F cosine of theta here. Okay. Then it should be okay because it's going to give you the same thing, WF net multiplied by the distance. So it should be the same thing, but if you neglect angle, then it could be an issue. Okay. Sometimes this equation creates some problem in understanding that this cosine of theta is linked to the force. It should come with the force, or it should come with the displacement, because that tells you that which direction your force is. You are taking the horizontal or the vertical value. Okay, so that has to be the part of it. Good, great work. Do you all know what he just asked? Do you all know what he just asked? Okay. Yeah. He said treat the forces separately, and then the vertical motion and the horizontal motion, and then come up with the answer. If you follow the directions properly, take the angle with them, then it should be okay. All right? But my recommendation would be do each work separately and then put them together. Here's another problem. It is slightly different from what we have done. It's on the inclined plane, and there is a hiker who is walking up the inclined plane with a backpack on. Obviously, I'm going to draw a person now with a bag. Okay, it's like a wings. He's about to fly. He just walk up the hill and then start flying. Okay, so he is walking up the stairs or hill. The height he reaches is 10 meter, his back, we would need his backpack back. The mass of the backpack is 15 kg. All right. His vertical displacement is 10 meter. Okay. Now, pay attention to that. He is going up the hill, which is inclined. His actual final vertical displacement is 10 meter. We are more interested in his backpack. We want to know what is the work done on the backpack. By him, by the hiker. Okay? How much work he is doing on that backpack. All right? Also, we want to know what is the work done on the backpack by the gravity. Because it's going against the gravity, so gravity would be some force which can affect it. Does it not something here? So displacement is here, d. Good. Starting from the bottom. The force he is applying is Fh. So I have excluded. So free body diagram, I'm excluding the backpack. Okay, I'm just putting the forces there. And then the gravity, the weight of the weight is downward. Does it seem about right? The picture? The force when we hold something, when we are carrying something, we apply a force upward. Correct? How much that force equal to? Do you know when I'm holding something, how much force I'm applying on that object? Yeah, equal to its weight. Okay? This is something we will use here. But it is the upward force by the hiker on the backpack equal to his backpack weight. Okay? This one, the force by the hiker on the backpack. If we give this angle a name theta, this would be 180 minus theta. Right? Good. If you imagine where this angle, where do I put this angle on this triangle? Use the bisecting lines, or not the bisecting, intersecting lines, and think about where should I put that theta on that triangle. Imagine which corner? This? Here? It does go on the top corner. So this is something, this angle, this triangle is actually here. I didn't make it complete, but this theta is actually here. So this angle goes at this point. And this one is called D. Well, it looks like I didn't draw the full line, but it's the total length of this inclined hill. Okay. So if we want to know the work done by the hiker, we have to have FH and D cosine of theta, right? Do we have D cosine of theta? Can we connect it to 10 meter? We don't have theta directly given to us. We don't know what theta is. There is no way we can find theta 2 unless we had at least one more length. We don't have it. But is there any way we could connect D and 10 meter? Because 10 meter is given. We don't. Anna? Anaya? See, I know some names now. Robert? No? But this is the answer I'm going to get from you. Is there any way we could link this 2 with this when we know theta? Yes. How? What if you draw perpendicular on the horizontal from D, from this end? What is this length equal to? F sine of theta. F sine of, no. Or, okay, what's this angle? This is 90 degree. What is this angle? Well, we don't know that. We don't know, it's not given. Oh, come. Sorry? 90 minus theta, can you figure out the angle? This length? What is it? Go on. 90 minus theta, correct. What is this length? D. Which one is the base? This? D cosine of 90 minus theta. What is this length? D sine of 90 minus theta. Good? That's all. What is cosine of 90 minus theta? That's trig information. Does the angle change? Cosine changes into? Come on, guys. Sine. When there is 90 degree angle, then the cosine will change into sine. So this is going to be d sine of theta. What about this? This changes into d cosine of theta. It's not positive negative because they both are in the first quadrant. 90 minus theta. So somehow I did get the answer from you. So d cosine of theta is equal to 10. FH 10 meters. See how we connected them. That's why I said that this question is a bit complicated, slightly more challenging because it's not giving you the angle directly and you don't even need it. FH is equal to mg multiplied by 10 meter. M is what? 15. 9.8 times 10. You just multiply them, get the total work done by the hiker, which is 1470. Could you tell me quickly what is the work done by the gravity? Everything remains the same. Sorry, say it again.
15 times 9.8.
And the angle? The same angle? Gravity is exactly opposite to this force. Right? So what is the final angle? By the way, the work done by the gravity is going to be exactly opposite. This is going to be minus 1470 joules because it's exactly opposite to the force that we are talking about. So whatever work that force has done for that displacement, the same work in magnitude will be done by the gravity but in opposite direction. You can further go into it, figure out the angles for the gravity and the displacement and get the answer, but no matter how you proceed, you should be getting the same answer because these two forces are exactly opposite. Everything else remains the same. Net work done will be 0. However, work done on the back by the hiker would be 1470. Net work done by all the forces, okay? Hiker, gravity that we included here, total net work done is 0. It's not accelerating, so there is no acceleration involved. The force remains constant, and the work done by these constant forces in all is 0. But still, there is overall work done by the hiker on the backpack. That's why it reaches to that height.